Okay, so this question deals with figure 1.3. Please ignore figure 1.2 here. Okay, so point travels along the x-axis with a velocity whose projection vx. Okay, so velocity vx is presented as a function of time by the plot in figure 1.3. So it's vx versus t. Okay, assuming the coordinate of the point x equal to 0 at the moment t equal to 0. Okay, draw the approximate time dependence plots for the acceleration wx, the x coordinate, and the distance covered s. Okay, so we will go one by one. So as you already know, the acceleration, which is wx here, uh, sorry, yeah, wx here will be equal to, acceleration is nothing but the rate of change of the velocity with respect to time. Okay, so of course we are dealing with magnitudes here. All right, so it will be of course dvx by dt. So basically it's the slopes of this particular curve in figure 1.3. Okay, so we need to draw it. So approximately, as you can see, wherever velocity is constant, that is from 1 to 3, and from, of course we'll, okay, let's consider that it is till 8, let's say. Okay, 7 to 8 the velocity is constant, so the acceleration will be 0. Wherever the slope is positive, of course, since acceleration is equal to the slope, acceleration is positive, where the slope is negative, acceleration is negative. Okay, fine. So now let's draw the curve. So it is wx versus t, right? And it's an approximate plot. So 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and so from 0 to 1 we can see that the slope is 1, so the acceleration will be 1, right? So from 0 to 1 the acceleration is 1. Okay, now from 1 to 3, t equal to 1 to t equal to 3, the acceleration drops to 0, right? Okay, now from 3 to 6, that is this part, 3 to 6, the slope is negative, and it is, if you observe, it is -1. So this is -1, so it will be from 3 to 6. Okay, so 3 to 6, 3 to 6, it is -1. Okay, yeah. Now from 6 to 7, right, 6 to 7, you see it is a positive slope, and the slope is actually 2, so it is 2. Let's say this is 2 roughly. So from 6 to 7 it is 2. So say, okay, from 6 to 7, right, it is 2, right? Of course, yeah, 6 to 7 it is 2, and then from 7 to 8 it suddenly again, since the velocity is 0, this is a constant velocity, it drops down to 0. This is basically the acceleration versus time plot done. This part is done. Now the x coordinate. The x coordinate is nothing but the displacement. So as you already know that displacement is nothing but the area under the vt curve, right? So starting from t equal to 0, we just keep finding out what is the area, and basically that's that. or in other words, if we want to find s at some t equal to t naught, that will be integral of v as a function of t dt from t equal to 0 to t equal to t naught. So everything is from t equal to 0. That's important. Okay, so now let's look at the curve. Wherever there is constant velocity, it is just simply, so area of curve is very easy to find. So basically the displacement varies linearly with time. Now when the velocity itself is varying linearly with time, there is constant acceleration. So in those cases, the curve will take the form of a parabola. Okay, we'll see how the equation turns out. Okay, since we already have the velocities and the accelerations from Vx and Wx versus t curves, I mean figure 1.3 is Vx versus t, and this figure is just now which we drew is Wx versus t. So we can easily find out s. So this is a very general equation. Otherwise, what we can do is, for this particular case, we can have sx some t equal to t naught. Okay, so that what we can do is, no, I guess we'll go step by step. Instead of, we'll take like we'll take some windows of time, and accordingly we'll keep calculating, right? So let's say from t equal to 0 to t equal to 1, t equal to 0 to t equal to 1, what's happening? So t equal to 0 to t equal to 1, the initial velocity u, only for that span, the u, okay, we'll actually, you know what, we'll have a general equation. I think that's better. So if we can divide first of all this curve figure 1.3, or basically the whole from 0 t equal to 0 to t equal to 8, you can divide it into certain spans. So for instance, from t equal to 0 to 1, it's basically a constant acceleration. From 1 to 3, it is constant velocity, right? From 3 to 6, again it's some constant acceleration, right? From 6 to 7 also it is some constant acceleration of some other magnitude, and from 7 to 8, of course, it's zero velocity. So I mean, whenever it is zero velocity, it means that basically the particle is not moving, right? All right, okay. So once we have these spans, what we can do is, for each span we can say that the s at some t equal to t naught, okay, is equal to s at some prior t equal to t dash, let's say, right? Okay, the displacement till that t dash plus, sorry, plus, so basically from t dash to t naught, let's say the time delta t, the time between t naught and t dash, let's say it is this. So s t equal to t naught is equal to s t equal to t dash plus u at t equal to t dash, okay, u at, I should have, it's not a function exactly, it is u at t equal to t dash into, so delta t, because, so I'm basically applying ut plus half at square, right? So for this delta t, basically we need to find out what is the distance. So u delta t plus half a, which I'll write it as w because that is the notation being used. W at w during this. Okay, this is important. This w basically represents the acceleration in this time period delta t. Okay, right, we are assuming that during this delta t the acceleration is a constant value. Okay, so I'm just writing it as w into delta t whole square. Okay, now so basically this is nothing but, this distance is nothing but the incremental distance, that displacement, sorry, this is nothing but the incremental displacement from t naught to, sorry, from t dash to t naught. That's what it is. So this equation makes sense now. Okay, so now for t equal to 0 to 1, right? So obviously your, if we assume that, so for everything what we'll do is we'll assume t dash to be the starting point, that is over 0, and t naught to be the ending point, that is 1, right? So we already know that initially the point is at x equal to 0. So s t equal to t naught, which is 1, is equal to st equal to t dash, which is 0, which is anyway 0, plus u at t equal to t dash. Initial u is, let's see from the curve, initial u is 0, right, from figure 1.3. So this term also becomes 0, right, plus half. So just remember one thing, since it is an approximate curve, I'll just find out the end points of, like, whenever it is a parabola, in this case it will be a parabola, because you have this acceleration due to which there comes this t delta t squared term. So because of this, basically the displacement varies with time, varies with the square of the time. So that is why the shape will be a parabola. But since they have asked us to draw an approximate curve, if we have the initial point and the ending point, we know the rough shape of the curve. It will be a parabola that is basically curved upwards. So you will see when I'll draw the curve. So half into, so what is the w during the delta t? So from this curve that I have drawn, it is 1. So half into 1 into delta t square. Delta t is, okay, yeah, of course, delta t is 1 minus 0, which is 1, right? So 1 square. So this becomes 0.5. Okay, so s at t equal to 1 is equal to 0.5. Fine, we'll draw this later, the whole curve. Now let's go to the next span. So it is t equal to 1 2 3, constant velocity, right? 1 2 3. So t dash equal to 1, t naught equal to 3, delta t equal to 2, right? And of course w is equal to 0 in this case. Just for completeness, in the first case w was 1, right? Okay, so s at t equal to 3 is basically s at t equal to t dash, which is t equal to t, s at t equal to 1, which is 0.5, right? Okay, plus ut. Okay, so u is basically the velocity at t equal to t dash, where t dash is 1. So at t equal to 1, the velocity over here is 1 from figure 1.3. So substitute 1 into delta t, which is 2, and since w is 0, this is basically, I shouldn't write it this way, it is 1 into 2, avoids confusion, sorry for that. So 2.5. So this becomes 2.5, right? And we know the shape. Okay, I'll just keep writing the shapes on the side, right? It will be, so this will be something like this will be a parabola, right, with slope that increases with time, because slope is the velocity and velocity increases with time from t equal to 0 to t equal to 1, because the acceleration is positive. For the from t equal to 1 to t equal to 3, the shape will be linear because it's constant velocity. Now time for t equal to 3 to, so you have from 3 to 6 you have some constant acceleration again. So t dash equal to 3, t naught equal to 6, delta t equal to 6 minus 3, which is 3, and w is, for this span, w is 3 to 6, it is minus 1. So since it is constant acceleration of negative magnitude, the shape will be a parabola with slope decreasing with time, right? All right, so now s t equal to 6 is, of course, s t equal to 3, basically the t dash, which is 2.5, plus u. So if we check the equation, velocity at t equal to t dash, which is 3. So what is the velocity at t equal to 3? So the velocity at t equal to 3 is 1, right? 1 into delta t is 3, 1 into 3, right, plus half, okay, so half into w is minus 1, delta t square, which is basically 3 square 9, right? This becomes 2.5 plus 3 minus 4.5, becomes 5.5 minus 4.5, which is 1. All right, yes, at t equal to 6 is equal to 1. Okay, so we have reached till 6, t equal to 6, then 6 to 7. Okay, now just a second, I will put separator so that there's no confusion. All right, okay, now t equal to 6 to 7, so t dash equal to 6, t naught equal to 7, delta t equals 7 minus 6, which is 1. W, if you see figure 1.3, or sorry, the hour figure, basically the W is 2. Okay, W is, now S at t equal to 7 is equal to S at t equal to t dash, which is 1, plus U at, plus if you see the formula, initially U at t equal to t dash, so U at t equal to 6, which was minus 2, right? Now it is minus 2 to delta t, which is 1, plus half into a, I mean acceleration w, 2 into delta t square, which is 1 square, so it becomes 1 minus 2, okay, 1 minus 2, again plus 1, so it is 0. So basically it comes back to the origin. Okay, that's what this means. Okay, so now we plot how will the curve look. And of course from t equal to 7 to 8, since the velocity is 0, I mean st equal to 8 is equal to st equal to 7 is equal to 0, stays there. Okay, now if we plot s versus t, right? So let's see, let's try it carefully. So just we need to remember one thing, that the slope is equal to the velocity. Okay, the slope of the st curve at any point t is the velocity at that particular time point. So from 0 to 1, obviously it is an increasing parabola, as we said, and the end point, that is st equal to 1, is 0.5. Okay, so 0.5, let's say this is 0.5, and let's say this is 1. So starts off with zero slope, of course, goes up, goes up, goes up, and it's roughly a parabola. Sorry if it's I mean, the drawing is not very good, but you get the idea, I guess. Now once you have this from 0 to 1, from 1 to 3 it's constant velocity, right? It's a constant velocity. And remember one thing, which is an important point while drawing these curves: the velocity remains constant. I mean, at 2, at 3, t, it is same as at t equal to 1. So basically what's happening is the slope is maintained. Okay, so slope is maintained. So at t equal to 3, the point is at 2.5. okay, t equal to 3, so this is t equal to 3, it is at 2.5. okay, so you'll have a tough time drawing this, something like this, let's say. So this basically, I'll redraw this part, this is looking really clumsy. Okay, so this is 2.5, let's say. Okay, let's say this is, yeah, this is over here, let's say, and of course 0.5, let's draw it as much as to scale as is possible. So this is, let's say, 0.5, which makes much more sense. All right, so now at t equal to 1, t equal to 0 it is at 0, t equal to 1 it is at 0.5, and right, and t equal to 3 it is at 2.5, right? So this is constant velocity, it goes like this. Now the velocity at t equal to 1, t equal to 2, t equal to 3 all are same. So over here also it will be, there will be no breaks in the slope basically. So essentially this will just smooth out, right? Goes like this and smooths out, right? Okay, fine. Now we have it till t equal to 3. Now what happens from 3 to 6? From 3 to 6, at 6, so if we draw it 4, 5, 6, t equal to 6, the point is at 1. Okay, so this somewhere around here, let's say. So right, t equal to 6, so it is somewhere over here. All right, now this is an interesting thing again. It's a parabola with slope decreasing with time, and note, if we observe figure 1.3, the velocity from 3 to 6, at 4 the velocity becomes 0. It is basically like the direction in which the body is going reverses, right? That is what is the velocity. So essentially, like at t equal to 4, the body stops, the particle stops, and then starts going in a reverse direction. So at t equal to 4, velocity becomes 0 means the slope becomes 0. So at t equal to 4, okay, let's t equal to 4, what happens? So the slope becomes 0, right, and starts decreasing after that, right? So it's a parabola where the slope decreases with time, as we said. All right, and at 6, t equal to 6, of course velocity is quite negative, that the slope is quite negative, which is -2. Okay, So now what happens after that? After that, there is again a sudden positive acceleration, right? And at t equal to 7, basically the point comes to us, becomes stationary and becomes back to the origin. So at 7, what happens? So at 7, what happens is, from t equal to 6 to t equal to 7, the of course, like the velocity of the body in the negative direction, the magnitude in the negative direction keeps on decreasing now. Okay, so t equal to 6 is basically where you have the maximum negative velocity or the maximum negative slope in case of the ST curve. So basically the slope over here is the maximum in magnitude in case of the negative direction. I mean, if we consider from 4 onwards, the body is going in a backward direction. So in that, the maximum magnitude of the slope is at t equal to 6, and of course at t equal to 7, the body comes to a stop, so the slope becomes 0. And of course it is a parabola with the slope, okay, this forward to right. So this is from t equal to 6 to 7, it is a parabola with slope increasing with time, because the acceleration is positive, slope is nothing but velocity, so velocity increases with time, so the slope increases with time. So the slope keeps on increasing till it becomes 0, right? So it essentially is okay, I changed the color, sorry for that. Yeah, so it essentially becomes something like this. Yes, right. Okay, and of course at 8 it is like still 0, right? Okay, so this is a rough curve of the displacement versus time. Okay, now next part is the distance covered s, okay, respect to time. So so here if you observe, the till t equal to 4, we see, okay, till t equal to 4, we can see that the velocity is positive, so it's going in the forward direction. So 4 is the point where it starts backing up. Okay, so how will we get the distance versus time curve? So what we just need to do is, so over here what is happening, uh, after t equal to 4, we are seeing the magnitude of the displacement starts decreasing. So essentially if we just have a mental picture, so this is, let's say, t equal to 0, this is just the, I mean, just a schematic of how the body is moving with respect to time. So let's say it starts moving at t equal to 0 in the right hand direction, at t equal to 4 it reverses its direction. So now after t equal to 4, if we see basically some distance displacement, this is, let's say, some s max, which is the maximum displacement over this time. So after this, okay, whatever is the, which is this basically the displacement from 4 t equal to 4 onwards, that is if we take t equal to 4 as the reference, it is negative, right, with respect to t equal to 4. obviously, because it's going in the backward direction. But if we consider the distance always adds up. So basically, okay, basically what, so if we consider this as this is the S max, right, and this is some x, right. So what this curve is basically, so after t equal to 4, right, this curve basically shows you S max minus x. This is the displacement, but distance would be S max plus x, right. Distance would be S max plus x, right. So basically it's nothing but, so with respect to S max, okay, with respect to S max over here, instead of minus x, so whatever decrement is, basically we have to increment that much. So it will be basically a reflection of this about this particular, you can say, you can mirror the curve after t equal to 4 with respect to this particular horizontal axis or horizontal line, I should say. So just need to mirror this. So it will be, so if I draw here it will be a bit clumsy. So essentially I'll just draw the shape. Of course we can find out the values. I'll just draw the rough shape that will be coming out of this. So it will be an increasing, obviously an increasing parabola initially, then constant velocity, then it will become 0 from this point onwards. Instead of a decreasing parabola, again it will just be a reflection, so it will again start increasing, right. Okay, and of course it will come to a halt after some time, right. This is basically t equal to 4, right, and this is, let's say, t equal to 1. This is constant velocity from t equal to 1 to 3, right. T equal to 1 to 3 is constant. Now t equal to 6 is sort of, so t equal to 6 is wherever you have the, after t equal to 4, t equal to 6 is where you have the maximum magnitude of the slope, okay, which is like basically somewhere around here, I suppose, right. This is t equal to 6, and t equal to 7, velocity again becomes 0, comes to a permanent halt, almost, as far as the information that we have, comes to a halt at t equal to 7. T equal to 8, it remains at that position. Yeah, essentially this is the curve. So of course if we did not calculate, we can easily calculate what it would be at t equal to 4, the distance. So we can either do the formula thing, or we can directly see from here that is from 0 to 4, the area under the curve, basically our S max, can be very easily found out from area under the curve of vxt, basically, so which is half into, this is area of trapezoid, height is 1 into a plus b, which is 4 plus 2, so this becomes 6 by 2, which is 3. This is S max, okay. So I'll just, this is S max is equal to 3. 3 is the, okay, maximum. So this is 3 essentially, okay. And obviously since it comes back, so this point over here, so it will be 6, right, because it comes back, so basically it covers a distance of 2 S max, right. Pretty simple. So yeah, so basically we got the curves for all the three. This is the curve for wx versus t, this is the curve for the x coordinate or s versus t, and this is over here is the rough approximate curve for the distance with respect to time. So thank you.